Okay. So, oh, hold on, interruption. Marcus just walked in late. Do we want to change our excuses or do we want to stay with those? Probably not going to fire off Wi-Fi issues, but let's find out. Why are you late to my class, Marcus?
I left too late.
He left too late. Interesting. Okay.
And Wi-Fi issues.
Oh, and he also had Wi-Fi issues. That's great. Awesome. Okay, so I'm sorry. What's that?
I killed 2 birds with 1 stone.
Yeah, very nice. Very nice. Okay, so we're going to get into concavity in the second derivative test. The second derivative test is not the biggest part of this lesson, and in fact, it's something I'm going to teach you, but you're probably never going to use it. Well, I shouldn't say never. You're seldomly going to use it. However, concavity is crucially important. So we'll save the second derivative test till the very end. Okay. So concavity, we're going to talk about what does it mean to be concave up and concave down. We're also going to talk about something called a point of inflection. We are going to then, at the very end, talk about the second derivative test. And then, of course, today, you should be able to roll your tongue, which I am incapable of. They tell me it's a genetic thing that you can either do it or you can't. I never learned. Yes, everybody? Roll your tongue?
Yeah,
Good.
I can't do that.
You can't do it? Okay, interesting. All right, so before I get into a bunch of calculus stuff, let me just draw a couple pictures for you of what concavity is. So concavity is the general shape of a curve. And there's 3 scenarios. Part of a curve is either going to be straight, which is not very exciting, or it's going to have a curve to it. That curve to it faces one of 2 directions. It's either going to curve up like that, or it's going to curve down like this. And there's 4 scenarios we're going to be concerned with. This is called concave up, but it's also increasing from what we talked about with the first derivative. Okay. So again, it's concave up. It's like a U shape, but the function itself is increasing. This one is concave up still, but it's decreasing. Does that make sense? Okay, good. Concave down and increasing, and concave down and decreasing. Okay. 5 possibilities. For concavity, we don't really care about this one too much. We're going to look at the other 4. And initially, what we're going to be most concerned about is just whether it's concave up or concave down. And I'll show you some calculus as to how we can get to that. Okay. This is the gist of the lesson. Are there any questions on this before I start getting into things in blue rectangles? No? We're good? Good here? Beautiful. Okay, so we are talking about the definition of concavity. This is the most useless thing I've ever included on a slideshow, but I put it in there just so I can say I gave it to you. Let's skip it. Here we go. Here's the first picture I drew. Concave upward and increasing. Okay. The reason I included this picture is I want you to look where the tangent lines are. All of the tangent lines in this concave up increasing function are below the actual function. Okay, so you understand what I'm saying by that? Yeah.
Yes.
Good. Let's go back to this picture then. We just looked at this one. But we can also look at the other 4 and see if we can recognize a pattern. Okay, so we'll start here in the lower left-hand corner. Concave down and increasing. Would the tangent lines be above the function or below the function? Above. Okay. Upper right. Concave up and decreasing. Above or below? Below. And then, last but not least, concave down and decreasing. Above or below? above. Okay, so what's the pattern here? If it's concave up, the tangent lines are always below the curve. If it's concave down, the tangent lines are always above the curve. I said that backwards, didn't I? Concave up, the tangent lines are below the curve. Concave down, the tangent lines are above the curve. So there's that one, then there's that one we talked about already. This will become relevant later on when we start looking at problems where we have to approximate functions based on the tangent line versus the function itself, but we got a ways to go for that. Okay, so here we go. Test for concavity. This is more practical than the last blue rectangle. If we want to know if a function is concave up or concave down, we're going to look at the, whoops. Okay, come on, Rita, you can do this. There we go. We're going to look at the second derivative. If the second derivative is positive, in other words, greater than 0, the function will be concave up. If the function is, second derivative is less than 0 or negative, it'll be concave down. The rest of what we're going to do is almost identical to what we did with the first derivative, with a couple changes, which I'll show you. Now, what do I mean by what we did with the first derivative? Well, if you'll recall, with the first derivative, we took the derivative, set it equal to 0, found the critical numbers, put them on a number line, tested some regions. Done. Exact same thing is going to happen here. So I want to know where this function is concave up and concave down. So we're going to cheat. Get out your graphing calculator, get out your Desmos, graph that cubic, and see from looking at the graph, can you determine where the function is concave up and where the function is concave down? So we should have an idea of what our answer is going to be, and then we'll do the math to see if we can get it to match. Okay, do you all see that part of this graph is concave up and part of this graph is concave down? Okay, good. Let's do some math then. So I took the first derivative. Easy peasy. Also remember, we're starting with a cubic. The first derivative will be a quadratic. The second derivative will be linear. So then we get it down. And by the way, this critical number stuff here for the first derivative is irrelevant. I was just showing off. Second derivative, 6x plus 2. Nice and easy. Set it equal to 0. And find the critical number. Okay, and I purposely chose an easy cubic so that A, you could visualize it, and B, we're not getting bogged down in the derivatives. We will get bogged down in the derivatives, just not on this one. And again, notice the process repeats itself. I have the second derivative. I found the critical number by setting it equal to 0. I slap it on a number line. And also, hey, what do you got?
No, I lied. I thought you were winning. I
No,
thought you were going to be the winner, but you're not.
5.
6 so far is the winner.
Ooh,
So close.
so close, but yet,
So far.
so far.
You know what they say. If you're not winning,
If you're not first, you're last.
if you're not winning, you're losing.
Yep.
You're a loser.
That gets you.
He's not real good on SEL, is he? Social emotional learning.
Yeah.
He doesn't care about my feelings.
No, he doesn't.
No. It's too bad he's my boss. Okay, what was I going to say? This guy. Remember how I was being a jerk about how you labeled the number lines and it seems like an irrelevant thing and I kept bringing it up over and over again? Well, now it becomes relevant because as we progress through these problems, we're going to have a first derivative number line But we're also going to have a second derivative number line, hence the f double prime. Put the critical number on the number line. Test regions. Now, when we test regions, I kind of glance over that, but again, this thing tells me where I'm plugging numbers into. So if I take something over here like, oh, I don't know, -4, and I put it into the function, I get a negative value. If I put something over here like 0 into that, get a positive value. And therefore, I get this. Now, notice the subtle differences here. No arrows. It's simply concave down and concave up. Because the value is negative, to the left of -1/3, it's going to be concave down. And to the right of 1/3, it's concave up. Does that match with your pictures? Yeah?
Yes.
Yeah, it's a standard, if I pick the problem right, it should be a standard cubic like that, right? Okay. Where this point is -1/3. So we need to talk about -1/3 because it's not, the critical number on the second derivative number line is not the same thing as the critical number on a first derivative number line. The first derivative number line, critical numbers, represent maxes and mins. Is -1/3 a max or a min? No. What is happening at -1/3?
Like the center of all of it, like right smack in the middle.
You have to speak louder so they can hear you and clarify a little bit more.
I don't know how to clarify it. It's like right in the middle of the graph. It's like what separates both of the concavities.
Good. Okay. Did you all hear him? He said it's what separates the concavities, which is perfect. But that has a fancy name, which we'll get to eventually. Okay? But again, the critical numbers on the second derivative are not maxes and mins. Very seldomly, if ever, will they be. Okay? So now let's try something a little bit more funner. Okay? Time to come off the porch and run with the big dogs. Same problem I just finished. However, I have a more interesting derivative and second derivative to take. So please tell me, after doing a bunch of derivatives, where that function is concave up and concave down. If you want to cheat first by looking at a picture, go ahead. But at some point, you have to show the math. Okay, go. What is there? 5 of you in here, right? Okay, so 5 of you in here, and how many? I'm doing some math here. 25 and 25 is 30 minus. Perfect. Everybody's here. Are you guys going to be okay if I walk around the room, or is it going to freak anybody out? We good? We're good. We're good. Just wanted to check. Don't want anybody to be uncomfortable. Are you doing a quotient rule or a product rule? Okay, good. Good. Max, quotient rule or product rule?
Quotient rule for both.
Quotient rule. Oh, no, there you go, product rule. Right?
Yeah, I did question.
You did quotient. Where did you do that?
Right there.
Oh, I see, okay, got it. You snuck it all into one line. What are you doing, quotient rule? Yeah. Good. Marcus? Okay. For you Zoomers, who's doing a quotient rule first? We'll ask that one first. Raise your hand if you're doing a quotient rule. Is anybody doing a product rule? Okay, cool. Don't matter none. Should get the same answer. Are you guys all group, what is today, group 2? It's 2 and 3 today, right?
Yeah.
Are you all group 2?
No, it's on group 1.
I'm
Oh, it's
ready.
two.
It's one and
was it yesterday 1 and 2 also?
Yeah, Monday, Tuesdays, 2 and 3.
Gotcha, okay. And all of you then are group 2?
Yeah.
2. John, you're group 2 also? Group 1, you're doubling down. Gotcha. Oh boy. Amanda, let's pick on you. This will be fun. Do you want to, well, probably not sharing your screen wouldn't work. Can you talk me through the 2 derivatives?
Sure. All right.
Amanda,
so
don't
I
sound
know
so
the product rule.
don't sound so happy
So-
about it, okay?
Ah, it's okay.
So I'm assuming you wrote this as 6.
The product rule.
Uh-huh.
Yeah.
Okay.
So then the first one would be 0 because it's the derivative of 6 is 0. So
Mm-hmm.
and then
I'm not even gonna write it.
6 times -1. This was a chain rule times x in parentheses x squared plus 3 to the -2 and then times 2x.
You'll notice when I was writing down what she was saying, I got a little overzealous with the parentheses. Better to put parentheses in where you don't need them versus not putting them. For instance, if these parentheses weren't here, we'd have a big problem. Because all of a sudden that becomes 6 minus 1, and we don't want to mistake that. Did you leave it in this form, or did you clean it up?
I cleaned it up.
Okay, so -12x times x squared plus 3 to the second power. That cleaning it up, or did you just leave it as -2?
No, I did that.
Okay, good. All right, F double prime. Wait, hold on, stop for a second. Note, wait 1 second. Amanda, wait 1 second. Sorry. Notice I'm not finding the critical numbers of the first derivative. I don't care about them right now. I don't care where there's maxes and mins. All we're doing is looking for concavity. Okay, back to you.
Okay, so in the numerator, I had x squared plus 3 squared times -12, and then minus -12x times 2 times x squared plus 3 in parentheses, and then times 2x. And then that was over x squared plus 3 to the 4th.
Ooh, so you got all fancies in your pantsies. You did the first one as a chain rule, but then you switched to quotient rule. Cool, cool. All right, good. Are we good with that? All right, so what's going to happen for a lot of you is you're going to be able to get to this point, but then hilarity ensues. Now you need to figure out how to simplify that thing to make it workable. So let me outline some of the options I have. I could multiply that whole numerator out. I could square the x squared plus 3. I could then multiply each of those terms by -12. Then come inside the brackets and do a whole bunch of gunk in there. However, there is another method which I like better. You don't necessarily need to do this, but from experience, I think this one works a little bit better, and I'm running out of room here. But I'm looking at these as 2 different terms. I've got the blue term, and I've got the black term. And I'm looking at those 2 terms, figuring out what do they have in common. Well, they've got a -12 in common, and they have an x squared plus 3 in common. And then we get back to the discussion we had earlier. I have two different exponents. I have an exponent raised to the second power or to the first. Remember, you always take the smaller exponent. So I'm going to leave that out in front. That's my common factor between those two terms. When I pull negative 12 times x squared plus 3 out of the blue term, I'm left with an x squared plus 3. Minus. When I pull a negative 12 and an x squared plus 3 out of the black term, I'm left with, it appears 4x squared. Which would then give me negative 12 times x squared plus 3 times negative 3x squared plus 3 all over x squared plus 3 to the fourth power. We're having fun, right? It's fun?
Yeah.
Fun, right? Okay, good. Boom, boom, boom. Okay, we're almost there. Critical numbers. Set that puppy equal to 0. Remember, critical numbers, two things. What makes the numerator equal to 0? Okay, so it's a little crowded here, but negative 3x squared plus 3 equals 0. And what makes it undefined? In other words, what makes the denominator equal to 0? X squared plus 3 equals 0. Questions so far? Everybody good?
I have quotient rule for both, and I got a completely different answer. So I'm just following this.
Does it look different? It could look different. If you get the same critical numbers, you're okay.
Yeah, I'm just waiting to see what critical.
Beautiful. Okay, let's talk about this puppy first. This puppy first. All right. Bethany, what do you notice about that x squared plus 3 being equal to 0?
I have no idea.
Come on, you can do this. Solve it. Tell me what you get.
It is negative 3 and then the square root of negative 3.
Does that bother you at all?
A little bit, yeah.
It should bother you a lot. Okay. Remember, this isn't advanced algebra. We don't deal with imaginary numbers. So when we get down to this, oh, that's bad. Doesn't apply. Okay, there is no solution for us there. Which is nice. We don't have to worry about it. But then we come over to this puppy. And let's see, bring the 3 over, divide by negative 3 divided by negative 3. So x would be equal to plus or minus 1. Here are my critical numbers. Okay, so the denominator in this function did not give me a critical number. I only have critical numbers from the numerator. Your numerator might look different than mine. It's okay. You might have multiplied it all out. You'll see when I click through my work that I've done already, my numerator will look differently. That's okay, as long as you get those critical numbers.
I got fourth root of positive 3 is mine.
You may have made a mistake.
Yeah.
Okay. Any questions on this before I erase? All right, good. Give me a second here. Cleaning up my mess. This is taking a lot longer than I thought. Okay. Okay, so there's first derivative, and then my second derivative looks like that. It doesn't matter. It's the same thing, just written differently, because I still got critical numbers at 1 and negative 1. To be honest, it's been a while since I did this. I think to get this, I actually multiplied the numerator out. I don't remember. I didn't factor things out. But again, it can take different forms as long as you get the same critical numbers. Okay. Again, then the process repeats itself. Put those numbers on a number line. Test regions. The book is really big on, if you use the book, I'm sure that many of you don't except to get problems, but the book is really big on making a chart. I'm not a chart fan. I like the number line method. Especially knowing where we're going, I find the number line method to be a lot easier. Okay? And then, of course, you should answer in interval notation. The function is concave up from negative infinity to negative 1, and from 1 to infinity, and it's concave down from negative 1 to 1. The other thing that becomes a common mistake is, remember, we're talking about the concavity of the original function. We're using the second derivative to talk about the concavity, but the concavity applies to the original function. Okay? Questions? Go.
I don't know if this is relevant, but why can't we just take like the first derivative since it represents this tangent lines?
Because the first derivative is going to give us maxes and mins. We're looking for the shape of the curve.
Oh, okay. So we
Okay.
can always.
So yeah, so you think about, it seems like they would be tied to each other, but I can do sneaky things like, okay, there's a max. It's concave down, but I can also do this. Okay, that's still a max, but now it's concave up.
Oh,
So I use the second derivative to come up with the general shape of the curve.
okay.
Okay, good. Any other questions? Hot diggity. Let's move on. That thing that Max talked about before, that transition point from concave down to concave up that we saw in the cubic, or from concave up to concave down, is what's called a point of inflection. Okay, there's a couple different ones. Concave up to concave down to concave up. Not a max, not a min. It's just that point floating partway through the graph where you make that transition. Make sense? Awesome. We've done all the hard work. How to find the points of inflection? Ridiculously simple. Am I going too fast, by the way, or are we okay? Okay. Good, good, good. Good. Okay. There's a bunch of calculus speak. Blah, 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 blah. Theorem 3.8, point of inflection. If C, f of C, is a point of inflection on the graph of f, then either f double prime of C equals 0 or f double prime does not exist. This bottom rectangle is a fancy way of saying points of inflections must be critical numbers for the second derivative. The dog golden retriever relationship we had with critical numbers and maxes and mins from the first derivative also applies here. All points of inflections are critical numbers. Not all critical numbers are points of inflection. Okay, good. All right, let's try a new one. So let's take about a 7-minute break. And in that 7 minutes, what I would like you to do is now look at a quartic, 4th degree power. Find out where that function is concave up and concave down, and see if it has any points of inflection. Okay? Questions? I will see you back here promptly at 10:30. So get the problem solved, get up, walk around, go get a snack, get something to drink, check your Wi-Fi, make sure it's working properly. In any order you'd like. Feel free to mix and match, but I'll see you back here in 7 minutes. Carry on. All right, they're muted. Now we can talk bad about them. Same goes for you guys. Once you get the problem solved, or if you want to stretch your legs first, take a lap, go get a drink, whatever you need to do. It's your time for 7 minutes. Or step out in the hallway and pour your drink down your face. Oh, that's embarrassing. Oh, it's all over my mask too. Ah!
Yeah, it's where the two are.
I just have two.
Not never mind.
Kaylee, are you going to Wisconsin, or are you just wearing the sweatshirt?
Just wearing a sweatshirt.
I understand. No interest in Wisconsin whatsoever?
I don't know, I haven't really started looking at schools yet.
Are you only a junior?
Yeah.
Oh, you got plenty of time. My daughter just texted me and said, "What's up?" I said, "I'm teaching about concavity and calculus," and she sent me the throw up emoji. She's been through calculus already. But she never had me for class. That's a big difference.
I don't think this is that bad.
It wasn't intended to be that bad. That's why, I mean, I used a nice simple polynomial so you can understand the concept before you get bogged down with the calculus of taking derivatives.
Wait, did you get 3 points? Did you get a 0?
Yeah, I got 2 points. X equals 2 and x equals 0.
Oh, where do you get the x equals 0?
If you were to put 0 in this, then it would be like 0 equals 0, so it'd be a correct number. And also the graph has a change in concavity of 0.
Oh, so you looked at the graph. You didn't notice that? That's not something.
Are you guys under control? Easy peasy?
Yeah.
Beautiful.
Or do we have to do it like, with the parentheses, like it's.
Interval notation?
Yeah,
Yes.
interval notation.
Yep. Indiana.
I applied.
And?
I haven't heard back yet.
It's a great school.
Yeah.
What do you want to study?
Business.
Oh, nice. Kelly School of Business.
Yeah.
That's where my daughter graduated with a business degree. That's
Yeah,
why
I
she,
applied like direct admission into them, so.
that's why she works at Target Corporate now.
Yeah,
It's cool. I love that campus.
it's really pretty.
When are you supposed to hear?
I think in like 2 weeks.
Oh, nice. Yeah, they have those, the what do I call it? Living Learning Centers. You know what that is?
Kind of.
So you have, if you get into Kelly, when you get into Kelly, you can join what they call a Living Learning Center. So you live in a dorm with other students that are also in Kelly. So you have like a support group with you, and then they have all kinds of fun activities and stuff like that for people that you see all day long anyways. But it's a good way to go.
Yeah.
Of course, that was pre-COVID, so I don't know how they're doing things now.
Yeah.
Hopefully by like next year, everything like the vaccine
Yeah, it's
distributed. I mean,
Let's hope.
So it had like, what, 90-something% effectiveness.
Yeah, but even, not to be a downer, but a lot of the professionals have said even if they have the vaccine, like right now, it'd still take upwards of 2 years to inoculate the entire country.
The entire country, yeah.
All right, let's do this. Dylan, you back yet? Could you pick a number 1 through 5, please?
3,
3, and then could you pick a number 1 through 5, please?
4,
4. Daniel, tell us what you did.
Alright, so first I took the derivative of x to the fourth minus 4x to the 3.
And got?
Third, and I got 4x cubed minus 12x squared.
Mm-hmm.
And then I took the derivative of that, and I got 12x squared minus 24x. And then I simplified that. I set it to 0. I set that function to 0. Simplified it to 12x and then x minus 2. And for the values, I had x equals 2 and x equals 0.
Rocking it so far. Keep going.
And add a number line of f double prime with the numbers 0 and 2.
I assume you put them in the correct numerical order.
Yeah.
Okay, great. You'd be surprised how many people don't.
And then, so for the, I don't know how to say it, like, I plugged in -1 and I got a positive value for that. And then I put in 1 and I got a negative value for that. And then I got a positive value when I plugged in 3.
Perfect. Okay, so we'll skip the, is it okay if we skip the interval stuff? I'm assuming you can all do that from the number line. I did want to comment, thank you, Danielle, that's perfect. I did want to comment on the transition from here to here. So some of you might be able to set 12x squared minus 24x equal to 0 and solve it. However, I would encourage you to turn it into a product because it makes testing numbers much easier. When he plugged in -1 here, plugging in -1 is a matter of looking at that and saying, okay, that'll be negative. This will be negative. A negative times a negative is positive. Bingo. He's good to go. Move on. That doesn't mean that you can't plug -1 into that, and especially if you have your calculator, you could put -1 in there easily. However, I would encourage you to write it as a product because I think it makes your life a lot easier. Okay. Beautiful. Now, notice, excuse me, 0 and 2 now become points of inflection. Why are they points of inflection? Because it's where the concavity changes. So when we were doing the first derivative test, we cared about whether the derivative changed from positive to negative or negative to positive. It gave us different results. Remember, if it goes from positive to negative, you get a maximum. If it goes from negative to positive, you get a minimum. It doesn't apply here. We don't care if it goes from concave up to concave down or concave down to concave up. All we care about is that it changes. Okay, so there are POIs at x equals 0 and 2 because, whoops, I can spell, because f double prime of x changes sign. Okay, That's it. I don't care if it goes concave up, concave down, or concave down to concave up. There's still going to be points of inflection. Good? Questions? Pretty easy? Yes? Awesome. Yep, got all that. Oh, yep, so great, fantastic. Got the same results. Good. Yep. Okay, thank you. Yeah, there. Oh, and there's a picture of it in case you wanted to know what that looked like. And you see that sometimes the points of inflection are just kind of floating there doing nothing. They're a little hard to find from a graph, but the calculus will show us where those will occur. Okay, we good? Now we get into this gray area of the second derivative test. And as I mentioned at the start of the lesson, most of you will not use the second derivative test because it's tricky. It requires a bunch of extra work that you'll find you don't really need to do. Okay? So follow me on this logic. If I have a function, I take the derivative, I find the critical numbers, I can then find the maxes and mins. Okay? That's using the first derivative test. If it goes from positive to negative, it's a max. If it goes from negative to positive, it's a min. The second derivative does the same thing, but it uses the second derivative. So the question is, well, why would I bother taking a second derivative to find something that I can already find from the first derivative? And the answer is, I don't know. Really, the only time you're going to use this is when you're specifically asked to take the second derivative test. And at some point, I'm going to have to ask you that on a test or a quiz. And at some point, the College Board could ask you that on the AP test. So I have to show this to you. You have to understand it, but it's not going to be the most practical thing. We're not going to do it a lot. Okay? So the second derivative test works like this. Let's suppose I have a function that's concave down, and I have a critical number on it. Okay, so that critical number is going to be where the tangent line equals 0. From my picture alone, I hope you would recognize that that must be a maximum. Okay, so what's happening here? Well, f prime, let's call this at the point A. F prime of A is equal to 0, because that's a critical number. And f double prime of A is going to be less than 0, negative in other words. If it's a critical number from the first derivative and the second derivative is negative, it will be a maximum. We flip that for the other one. Okay, min. We'll call this point B. If f prime of B is equal to 0 and f double prime of B is greater than 0, then we get a min. Okay, I know you're confused. I know this is silly because we're going to do this anyways with the first derivative. But again, I just need to show you this, have you practice it a little bit, just so you understand when somebody says to you, use the second derivative to find the critical numbers. So it's shifting gears here, and again, this is what gets confusing. Up until this point, we've used the second derivative talking about concavity and points of inflection. Now, all of a sudden, we're going to put that concavity and points of inflection aside and use it to do what we can already do, and that is find critical numbers. Okay? So, the only thing I want to point out in this is this little guy down here in the little comment. The first derivative test always works. Okay? It will allow you to find maxes and mins. However, the second derivative doesn't always work. Second derivative test, I should say. If the second derivative test equals 0, then you're out of luck and you got to go back to the first derivative test. So again, why would I use a system that doesn't always work if I'm just going to go back to the first system that I already know? And again, I don't have an answer for you. So let's try one. I ramped things up a little bit. We went from a cubic to a quartic to a quintic. Okay. And I'm not gonna, what am I trying to say? I'm gonna work through this one so you can see what it looks like. I don't want to just cut you loose because I think you'll end up doing a bunch of work that you don't need to do. Okay? So here's what it looks like. I need to start by finding the first derivative. Easy peasy. Then I need to find the critical numbers. Those critical numbers happen at -1, 0, and 1. So again, for the 9th time, let me go through this again. If we were looking for a max and min using the first derivative test, then I would take these numbers here, put them on a number line, test regions, max mins, good to go. Well, that's not what we're doing. We're using the second derivative test. But I do know that each one of these points tell me the same thing. F prime of -1 equals 0, F prime of 0 equals 0, and F prime of 1 equals 0. Because that's what makes them critical numbers. Now I have to get the second derivative involved. So I took the second derivative. And cleaned it up a little bit. Now what I want to know is F double prime of -1 positive or negative? Okay, F double prime, try that again. F double prime of -1, is it positive or negative? Well, this would be, that's a negative. -1 in there would be that would be a negative, therefore it's greater than 0, so it's positive. Okay, so now I can apply the second derivative test. I have a function that's concave up, it's in the shape of a U, and I have a critical number, so therefore I must have a min. So this is going to give me a min. Let me stop there for a second. Is everybody following what I'm doing here? Little confused?
Yeah.
Okay, so let's look at these two chunks of information. This and this. And that's what we're going to combine for the second derivative test. So this says I have a critical number. It's either this or it's this. Is it a max or is it a min? This, F double prime being greater than 0, means that it is concave up, which means now all of a sudden it's this guy, which makes it a minimum. Okay? It's a U, and a U has a bottom, so it's got to be a minimum. Okay? Let me do another one and see if it makes sense. Let's talk about F double prime of 1. F double prime of 1. Whoops. Is it bigger or smaller than 0? That's a positive times a negative, which makes it negative, so it's less than 0. It's a negative value, which means I have an upside down parabola, and an upside down parabola has a max. So this is a max. It's a critical number from the first derivative. It's concave down. It's the upside down U. Therefore, we're talking about a hill, not a valley, and the hill would have a max. I saved the worst for last. What about 0? Well, F double prime of 0 is equal to 0, which means absolutely nothing. I cannot determine if 0 is a max or a min using the second derivative test. I'd have to go back to the first derivative test. And the reason I chose this quintic was because it shows you all three examples. Okay, so you have to figure out how you're going to work this. Are you just going to go back to, sorry, I know some of you are writing. Are you just going to go back to this picture and memorize that if the first derivative is 0 and the second derivative is negative, it's a max? Or are you going to use some visualizations? Concave up gives you a U. A U has a bottom, which is a min. Therefore, we have a min. Concave down gives you a hill. Therefore, a hill has a top, which must be a max. I don't know if you at home can see these awesome visuals I'm using, but you get the idea. Okay. The other thing is you have your notes all the time, so just make sure you have it in your notes. All right, questions on this? Go.
Yeah, I'm confused like why you plugged in the stuff for the F prime instead of just going right to the F double prime.
Because I need to know where the critical numbers are.
Yeah, but don't you already know because you have x equals like -1, 0, and 1?
Yeah, I got that from the first derivative.
Oh, okay.
So then I go on to second derivative to test those critical numbers. Otherwise, I have no numbers to plug in.
Yeah, but like when you did like the f like prime of negative 1 equals 0, like why'd you do that?
I just rewrote it to show you what we already found here.
Oh, okay, so
Yeah.
I already
Yeah.
did
Because remember, the second derivative test has two components to it. F prime is equal to 0, and then F double prime is either positive or negative.
that. Oh, okay. So
Okay.
we didn't do this.
Yep. And pretty much this is what we already said. Okay, and we talked about 0, and then, yeah, there's that, yeah, we did that, okay. Notice that this, I threw this in here just because I was feeling fancies in my pantsies, has absolutely nothing to do with the problem we just finished. I don't care where it's concave up and concave down. I don't care about the points of inflection. All I'm doing is using the second derivative to find the maxes and mins.
So both the derivative tests are used to find maxes and mins.
Well said. For those of you who didn't hear him, Max just said, so both of the derivative tests are used to find maxes and mins. And the answer is yes.
When would you use one over the other?
His other question for those of you that can't hear is when would you use one over the other? I personally would use the first derivative test whenever possible.
Okay.
Because it makes more sense to me. It's less work. Again, the only time you're really going to use a second derivative test is when your idiot teacher asks you to use the second derivative test on this one problem on this next quiz.
So there's like no real reason to.
It's just a different way to approach a problem.
Okay. And then the concave, like, what do they call that? The concave?
Concavity.
Concavity? We just
That's
use that.
important
Okay.
because that'll help you with the shape of the curve.
Okay.
Okay, so there's a picture of it, and we're done. Now, let's talk about where we're going here. We have enough tools now. Let's back up. Last year in pre-calc, you did some curve sketching, also known as graphing. And you drew some graphs of some pretty weird functions that you probably hadn't seen before. But there were certain limiting aspects to that graph. You didn't necessarily know how high the hills and valleys are. Now with calculus, we can get much more exact. Eventually, we're going to be putting all of this together and drawing very accurate graphs of weird polynomial and even non-polynomial functions using the calculus that we now know. So we can determine maxes and mins on a function. We can determine asymptotes, vertical and horizontal. We can determine points of inflection. All the things that you couldn't do last year, we can now do. So that's in the future. Okay? Questions about any of this? Beautiful. Give me a second here to stop my recording.